Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone. So, this study we have completed the lens maker formula, and today I am going to start our class with a numerical here. A convex lens of diffractive index 1.5 has a focal length of 18 centimeter. Okay, so here we have given a convex lens. So, make the important related diagram here related to the question. So, first we have a convex lens. So, we have this one as a convex lens, and the refractive index is 1.5. This means outside medium may be air. So this is mu a. So mu a equals to 1, and inside it is mu g. So mu g equals to 1.5. Okay. So as outside medium is air, so the relative refractive index a mu g is also equals to 1.5, because with respect to air, the absolute refractive index is counted as the relative refractive index. Okay. Now previously it has been given, it has a focal length of 18 centimeter. So as it is convex lens, so focal length we have given equals to 18 centimeter. Fine. In air, 18 centimeter in air. Calculate the change in its focal length when it is immersed in a water with refractive index 4 by 3. Okay. So check here. If you're talking about the medium, for previous case, mu1 equals to 1 and mu2 equals to what? 1.5. Clear or not clear? Now, what is the formula for lens maker's formula? So, it is equals to 1 upon f equals to mu minus 1, 1 mu 2 minus 1, right? 1 upon r1 minus 1 upon r2. Clear or not clear? So, 1 mu 2 minus 1 minus 1 upon r1 minus 1 upon r2. This is relative refractive index 1 mu 2 minus 1. Clear or not clear? Okay. More better, you can write it like 1 upon f equals to mu 2 upon mu 1, mu 2 upon mu 1. So it is equals to mu 2 upon mu 1 minus 1, 1 upon r1 minus 1 upon r2. Fine. For the first case, here we have two cases. So first case, the refraction is taking place from air to glass. Air to glass. Clear? So for focal length in air, yes, out as the outside medium is air, so you can write for the focal length in air, refractive index equals to mu 2 upon mu 1. So here we have given the refractive index of glass is 1.5. So one you can write 1 upon 5 upon 1 minus 1, 1 upon r1 minus 1 upon r2. Yes, can we write like this? This is equation number 1. Okay. Now, when you place some liquid, you have inserted your glass inside the liquid, then what will happen? As you inserted your glass inside the liquid will be outside medium. So, mu1 becomes the liquid medium. So, mu1 equals to your liquid medium. So, mu2 upon mu1. Mu2 will be remain same. As it is refractive index is 1.5. But the mu1 here have a refractive index as 4 by 3. Clear? So you have to place here 4 by 3 minus 1, 1 upon R1 minus 1 upon R2. Clear, students? So focal length in air is given how much? 18 centimeter. Okay, we are going to put that. So just divide 1 divided by 2. Now on 1 divided by 2, what will happen? So it will be 1 upon F air divided by 1 upon of F liquid equals to 1 upon 5 minus 1, 1.5 minus 1, and divided by 1.5 divided by 4 by 3. So 3 comes upside, 1.5 into 3, 4.5 divided by 4, right? 4.5 divided by 4 minus 1 and 1 upon R1 minus 1 upon R2. Here it is also 1 upon R1 minus 1 upon R2. Clear? They both cancel each other. Y- Yes. Now it becomes FL goes upside. So frequency, not frequency, focal length in the liquid upon focal length in air equals to how much it will be? 0.5. 1.5 minus 1 equals to 0.5. Right, students? And 0.5 you can write 1 by 2. So it is equals to 1 by 2. Clear? And this will be 4.5 minus 4 if you solve this one. So this will be 4.5 minus 4 divided by 4. So this is equals to 0.5 out of 4. Clear or not? 0.5 by 4. Yes or no? So it is equals to 0.5 by 4. May I write this 0.5 by 4? Okay. So 0.5 equals to how much? 1 upon 2, and here it is equals to 4. So it will become 1 by 8. So more better, we can write it equals to 1 by 8. Understood or not? 0.5 becomes 1 by 2. So 2 into 4 equals to 8. So it will become 1 by 8. Clear? Now FL, focal length in liquid, upon focal length in air, it is given how much? 18 centimeter. Yes, in the question it is 18 centimeter equals to 1 upon 2, and this comes on the numerator side. So 8 upon 1, 2 4 ja 8. So focal length is upon 18. Focal length in the liquid upon 18 equals to 4. So F liquid equals to 18 into 4. So it must be 72 centimeter. Let us check the answer. Yes. Okay, correct. So it is equals to 72 centimeter. But question is asked that what is the difference between the old focal length and new focal length in the both the medium? So new focal length in liquid medium, and previously it was in air. So the new one equals to 72 centimeter, and the old one it was 18 centimeter. So your answer equals to 54 centimeter. Okay. So it is equals to 54 centimeter. Done. Okay. So student, the difference of the focal length here, okay, is equals to 54 centimeter. Okay, students. So we're starting our next topic is linear magnification produced by a lens. So it is denoted by small m. So as in the case of mirror, we have seen the mirror in the case of mirror magnification was m is equals to height of image h dash upon height of object equals to minus of v by u. Yes. Similarly, in the case of lens, the magnification produced by lens equals to h dash upon h. This is equals to height of image or size of image divided by height of object. Clear? And it is numerically it comes equals to v by u, distance of image from optical center divided by distance of object. Hmm. So the linear magnification produced by a lens is defined as the ratio of the size of the image to the size of the object O. It is represented by the letter small m. M equal to size of the image, that is equal to a dash b dash upon size of object, that is equals to ab. It is given by I upon O. Okay. Now make a ray diagram here, like an object of length AB is placed front of the lens. So after the refraction, you will have an image as A dash B dash. Now you have in a convex lens, when image formed is real, as shown in figure, then use the concept of similarity in these two triangles. We have these two triangles. So A dash B dash upon AB, perpendicular upon perpendicular, equal to base upon base. So A dash B dash upon AB, this is the ratios for perpendicular, and this is equals to what? CB dash upon CB, right? Perpendicular upon perpendicular equal to base upon base. So A dash B dash upon AB is what? A dash B dash is your image. है ना? So A dash B dash equals to minus I upon plus O, because A dash B dash is downside, so it will be considered as minus I upon O is equals to CV dash equal to plus V upon U. Now you can cancel minus and minus sign both the side. You will have I upon O equal to V upon U. Clear? So this is the first case. For the real images, we have magnification equals to V upon U. Now for the second case, when the images form is virtual, then what happened? When the image is virtual, then again it is equals to A dash B dash upon AB and equals to CB dash upon CB, and I upon O equals to minus V upon minus U, because both the distances are left side of the ray. So both are negative. So negative and negative sign will cancel. So M up equals to I upon O equals to V upon U. It means no impact whether the image is real or real or inverted. We will have the same formula for magnification. M equals to I upon O equal to V upon U. Got it? Thus, in a convex lens, linear magnification is positive when the image is formed as virtual, and linear magnification is negative when the image formed is real. Remember, when your when your image is virtual, M is equals to positive for virtual image, virtual and erect image, and M will be negative for real and inverted image. Got it? For real and inverted image, M will be negative. Next, magnification by concave lens, sorry. So in the concave lens, images formed is always virtual. There is only one case in the case of concave lens. You know this one? In the case of concave lens, what happening? They say this is the convex lens. Here it is, optical center, O. Suppose this is your object. This one is your object. Okay. Anywhere it is placed, then what happened? First ray that is getting parallel to the principal axis, after the refraction it get diverged like this. Okay, and it is looking like that is coming from that point, some point, that is called focus. Clear or not clear? Yes, it is appear to be come from that point. It is called focus, where the first ray that is getting parallel, second ray that is passing from the optical center without any deviation, it passes through. Here you will be have image. This is called, if this point is A and this point is B. So the pin one is called A dash and this is B dash. So this is the image. So student, in the case of concave mirror, when your object is anywhere, okay, other than infinite, then there your image is formed, virtual image, okay, and between optical center and focus, and it is virtual, erect and diminished. You will have a small sized image compared to the uh, object. Okay, now in concave lens, image formed is always virtual as shown in the figure. So now check the diagram here. A dash B dash size of image upon size of object AB is equals to CB dash upon CB. So it is again minus V upon U, minus and minus get cancelled out, and M you have M equals to I upon O equals to V upon U. So what you observe, in all the three cases, we have the value of M equals to I upon O equals to V upon U. So hence the linear magnification in the case of a concave lens is always positive. Clear? So for the concave lens, because I is positive also, that is upside, and O is also positive, so positive upon positive equal to positive. Clear? As it is virtual and direct image, so and the value of M will be positive for the case of concave lens. Now next thing, power of a lens. So simple, power of a lens. What is power of a lens? When a lens is said to be more powerful. Here I am giving you two situations. A lens first is here and second is here. Lens L1, lens L2. This one is the optical center. and second one this one. Now when the rays are coming for the first lens, it works like this and focusing the rays at a large distance. Okay, so it having this one is focus. And second lens, when the rays are coming, it focusing at very short distance. Now tell me which lens is looking more powerful, the second one lens L2 or the first lens L1? Which is more powerful? No. You see the first lens having less ability to bend the rays and this lens having the tremendous and high ability to bend the rays. Yes or no? It's focusing in very less distance. Means the length of focus is very less. So this focus point is very close to the lens. Means focal length is small. And here this lens focal length is greater. Okay, focus point is far away as compared to the second one. Means its bending ability is less and its bending ability is high. Okay, so powerful lens means higher bending ability. The ability of a lens to converge a beam of light falling on the lens is called power of a lens. What is power of lens? It is the ability to converge a beam of light falling on it. Okay, that's called power of a lens. It is measured as reciprocal of the focal length. Shorter will be the focal length, larger will be the power. Here in the diagram, you check here. The focal length is small, means the power will be high. And here the focal length is greater, so the power of the lens will be less. Clear or not clear? Yes. For the convex lens, focal length is positive. So for convex lens, power is also positive. And for a concave lens, focal length is negative, so power is also negative. Clear or not clear? Means for convex lens, power will be positive. P for convex equals to positive, and P for concave will be negative. Clear or not clear? Convex lens power will be positive and concave lens power will be negative. Yes. So now P equals to 1 by F and unit of power as the formula for power is equals to 1 upon focal length. SI unit of focal length is equals to meter. So the unit of focal length is meter. So it will be meter 1 upon meter and the 1 upon meter is called diopter. Okay, so the SI unit of power is diopter. Yes. So what is one diopter? Uh, one diopter. If you want to define one diopter means if a lens having a focal length of 1 meter, if a lens can focus the parallel rays up to a distance of 1 meter, 1 meter, then power is equals to 1 upon 1 meter. It becomes one diopter. Clear or not clear? If a lens can focus the rays coming parallel to it at a distance of 1 meter, okay, it gives a sharp image of the image parallel to it, incident parallel to it at a distance of 1 meter or 100 centimeter, then the power of the lens is said to be 1 diopter. Clear? Okay. Formula for power, as we have the formula 1 upon f equals to 1 mu 2 minus r 1 upon f. We just derive by lens makers formula. It is equals to 1 mu 2 minus 1 upon r1 minus 1 upon r2. Now 1 upon f, you can replace this 1 upon f by p. So p is equals to 1 mu 2 minus 1 upon r1 minus 1 upon r2. Clear? This becomes the power of the lens. Got it? For a converging lens or convex lens, power is positive as I said. And for a diverging lens or concave lens, power is negative. The SI unit of power is what? Diopter. Clear? The SI unit of power is diopter. Diopter, as I said, what is the one diopter? When the power of a lens, focal length is, the power of a lens with a focal length 1 meter is called the lens having a power of 1 diopter. Now, when your power is in centimeter, so you must have to convert it is in centimeter. So whenever you have given your power is in centimeter, like you have to find power of a convex lens having its focal length on 25 centimeter. Clear? So you have to find the power. And the formula for power is equals to 1 upon f, and f is given here how much? 25 centimeter. So you must have to convert it in the meter. So 25 centimeter equals to 25 upon 100 meter. So this 25 1 ja 25 and 25 4 is 100. So power equals to 1 upon 1 by 4 diopter. You have converted into the form of meter, so it will become diopter. Clear or not? Okay, more better. You can write it like this. Whenever f is given in centimeters, so first you have to do convert in meter. So it will become 1 upon f divided by 100 meter, because 1 meter 1 centimeter equal to 1 by 100. So power is equals to 100 upside goes upside upon f in centimeter, and this become diopter. Clear or not clear? So here power is equals to 100 upon 25, as it is given in centimeter. So your formula will be 100 by f. Now cancel this one. So it will become 4 diopter. Clear or not? So power of a lens having its focal length equals to 4 centimeter. Sorry, 25 centimeter equals to how much? 4 diopter. Clear? Lesser will be the focal length, greater will be the power. So power, if the formula for centimeter equals to 100 by f. Yes. Let us take an example. Find the radius of a curvature of a convex. Find the radius of curvature of a convex surface of a plano-convex lens. Plano-convex lens whose focal length is 0.3 meter. Clear? So you have a plano-convex, means the major part of this is convex and the another part is plano. Yes, so this is the first part, this is convex, and another part here it is plane. Clear? So this is a plano convex lens. So numerical is like this. You have a plano convex lens. So this is the convex part and this is the plane part. What you have to do? Find the radius of curvature of a convex surface. So convex surface having some radius of curvature, certainly it is R1. Okay, now what? And whose focal length is given 0.3 and mu is equals to 1.5. The refractive index of the medium mu equals to 1.3, and mu equals to 1.3, and focal length is equals to 0.3. The whole total focal length equals to 0.3. Yes, let us find R1. Okay, it should having some R2. You also take care about this R2. Now find this. Okay, how to solve it, students? Yes, we have to find the radius of curvature of this, our lens one part, this convex part. Okay, so we have the formula for the lens. 1 upon f is equals to lens maker's formula. 1 upon f equals to mu minus 1 upon mu minus 1, 1 upon r1 minus 1 upon r2. Clear or not? We have been given the focal length equals to 0.3. So make here place the value 1 upon 0.3. Mu refractive index is given 1.3. So it is equal to 1.3 minus 1. Now in the lens, during the lens maker's formula, you know where is R1? This distance is R1. Yes or no? And here this one part, the right, it is R2. Clear or not clear? Now the R1 for this part, what is R1 here? This is behaves like a flat surface, okay, transparent slab. And where is the focal length of transparent? Transparent slab passes all the light, perpendicular light, undeviated. So you can consider that the focal length, sorry, radius of curvature is at infinity. For a flat surface, where is center of curvature? It will be up to infinity. Yes or no? So you can place here, it is equals to 1 upon infinity minus 1 upon R2. Yes, this is for R2. Radius of curvature for the second lens you have to find. So consider as R2. Now it will be 1 upon 0.3. Yes, check it from the solution. Yes, clear. So 1 upon 0.3 equals to 1.5 minus 1. So 1 upon 0.3 equals to 1.3. It is 1.5. Yes, I have made a mistake here. We have to take it 1.5. No problem, just change it. Okay, so refractive index is equals to 1.5. It is not 1.3. Okay, mistake is there. So make it 1.5 minus 1. So it will become beta 0.5. Clear or not? 1 upon 5 becomes 1 upon infinite becomes 0 because infinity is a very large number, and when you divide it, it will become 0. Clear? 1 upon 0 equals to infinity, and infinity comes here, 0 will come here. So it is equals to 0 minus 1 upon R2. Okay. So now 1 upon 0.3, make a decimal break here. So this will be 3, here it is 10. 1 upon 5, 0.5 becomes 1 by 2 minus 1 upon R2. Now solve this, you will have the value of R2 is equals to 0.15 meter. Clear? So radius of curvature R2 is equals to minus 0.15 meter. Done. Okay, write it. It is equals to minus 0.15 meter. Okay, students, let us perform a standard problem here. And very important problem. You are given the three lenses L1, L2, and L3, each of the focal length 10 centimeters. So remember, each of the lens having the focal length 10 centimeter. An object is kept at a 15 centimeter in front of lens L1. So see, here the focal length of the lens equals to 15 centimeter, and your object is at 15 centimeter, means it will have a real image because it is not between its focal and optical center. Clear? So first you find the V for the first object, this one object. Whenever U equals to 15, you have to, for the first lens L1, 1 upon F1 equal to 1 upon V1 minus U1. So you have find, just placing the values, focal length equals to, tell U equals to minus 15. You will have V1 is equals to 30. Clear? So first you have this V1 equals to 30. An object is kept at 15 centimeter front of it of lens L1 as shown in figure. The final real image is formed at the focus of I3. Yes. It is saying that the final image is formed at focus of I3. Yes. So this is the focus of I3, and it will be at 10 centimeter from the lens. Find the separation between lens L1, L2 and L3. So you have to find the distance between here to here and here to here. Clear or not clear? Okay. So whenever you have V1 is equals to 30 centimeter, V1 is equals to 30 centimeter means distance of image from the lens L1 equals to 30 centimeter. Clear or not clear? So, the focal length for this lens is also 10 centimeter. So, apply the formula uh, for 1 upon uh, for this lens. Okay, L3. So, the distance of the image from L1 is equals to 30 centimeter. For the lens L3, 1 upon F3 equals to 1 upon V3 minus 1 upon U3. You have given for this lens F3 is equals to 10 centimeter, and V3 is also given 10 centimeter. Clear or not clear? Means your image is formed at focus, then definitely you will be at infinity, because whenever u equals to infinity, your source is at infinity, then you will have your image at focus. So you can do it by this method, 1 upon f equal to 1 upon v minus 1 upon u. So just place the value, v3 equals to 10 centimeter and f3 equals to 10 centimeter. You will have u3 equals to infinity. Clear or not clear? Okay, means the rays coming are parallel. On the lens 3, the rays coming are parallel. Whenever the rays will come here on this lens will be parallel, only one case, when image, when the object is at focus. Means definitely the image here that is formed at a 30 centimeter, we have got from the situation number 1, V1 is at 30 centimeter. For the second lens, this point is work, this the image is work as object, okay, situated at the point of focus, means definitely this has to be how much? 10 centimeter. Clear? Because the point of focus is equals to 10 centimeter. Then after it, uh, if it is in focus, the rays are getting parallel after the refraction. Yes or no? So, what is the distance? 30 plus 10 equals to 40. 30 plus 10 equals to 40. Clear? Hmm. So, the refracted rays from the L2 becomes parallel to the principal axis. It is possible only when the image formed by L1 lies at the first focus of L2, that is at a distance of 10 centimeter from the L2. So separation between L1 and L2 becomes 30 plus 10 equals to 40. Now the rays are parallel, so it can have any distance because parallel rays are always parallel. So no effective changing this distance. Okay, so distance between L2 and L3 can be anything. Okay, so distance between L2 and L3 can have may take any value. Fine, noted. Okay, students, so we are moving our next topic is combination of thin lenses in contact and then reflection of light through a prism. So combination of lenses. So combination of lenses in various optical instrument, two or more lenses are combined together. Okay, to what? First increases magnification of image. So first objective is to increase the magnification. Second, to make the final image erect with respect to object. Okay, means like your first lens will provided you the inverted image, and again you use this lens, so it will provided again inverted, and inverted one time plus two time will give you a erect image. And third, reduce certain aberrations. That is, what are aberrations? Aberrations, not aberrations. The aberrations are defect of image by single lens. Some defects are there in a or image formed by the lenses. So to remove them, you have to use the combination of lenses, and you will finally your image will be sharp enough. So to obtain the position, size, and nature of the final image produced by a combination of lenses, we first find the image of the object formed by the first lens. Means to deal with the problem of this combination of lenses, actually there is a first lens. Okay, so you have to made the image of a given object by using your first lens. Now what will happen? The image made by the first lens, like this is the image made by the first lens. Somehow here is the image. So the image made by the first lens work as a object for the second lens. Yes. So this image made by the first lens, like in lens maker's formula, the intermediate image is work as a object for second lens. Understood? Okay. So same concept will going here. The image the to obtain the position, size, and nature of the final image produced by a combination of lenses, we first find the image of the object formed by the first lens. This image act as an object for the second lens and locate its image. The image formed by the second lens serves as the object for the third lens. Yes, if there is three lenses, there are three lenses, then the image formed by the third lens will behave like a object for the third lens and so on. Okay, so now for the two lenses, we are here to find the focal length of the equivalent lens. Like you having a two lens, f1 and f2 individual focal length. This is the first length having a focal length f1, and this is the second lens with focal length f2, and you have to find the focal length of the combination. So the final derivation you will have 1 upon f equals to 1 upon f1 plus 1 upon f2. In the terms of you can say power, so total power it becomes p1 plus p2. Clear or not? Now we are going to derive. So first condition when the both lenses are convex. Now see, C1 and C2 are the two optical center for the two given thin convex lenses L1 and L2 held coaxially in contact with each other in air. Suppose f1 and f2 are their individual focal length. Now, what happen when there is a point object? First, it has to refract through the lens L1 and consider for L1 it having the image at I1, I dash. Clear or not clear? Yes. For L1, your image, final image at I dash for L1 only. Clear or not? Okay. So let a point object O be placed on the common principal axis of the common principal axis at a distance OC1. So this becomes U. Yes, OC1 equals to U and forms the image is C1 I dash. This becomes V dash. This distance equals to V dash. Image distance for the first lens. Clear? So apply the formula by the lens formula 1 upon V dash minus 1 upon U object distance equals to 1 upon F1. Clear or not? So what we have the formula for the first lens 1 upon V dash minus 1 upon U equals to 1 upon F1. This is first lens formula for the first lens. Now I dash would serve as a virtual object for the lens L2. So this means this I dash the I dash work as an object for the second lens L2. Okay. So for the second lens L2, this I dash is work as a virtual object and this will work I final image I is its real image. Okay. Two time refraction will be there. First lens gives some convergence. Then after second lens will also give some convergence and your final image is I. So I dash would serve as a virtual image for the lens L2, which forms the final image I at a distance C to I. Final distance of the image is equals to C to I, that is V. Okay. So U equal to C2 I dash and C2 I dash and C2 I dash is near about C1 I dash as the aperture are very small. So C2 I dash is equals to C1 I dash. So C2 I dash, this V dash is called object distance. So apply the formula. What is the formula again? Apply the formula, lens formula for the lens C2, second lens L2. 1 upon V minus 1 upon U is equals to 1 upon F. So for the second lens, your final image is at V minus your object is equals to what? It is in the direction of the image. So it is equals to V dash equals to 1 upon F2. Clear or not clear? So 1 upon V minus 1 upon V dash equals to 1 upon F2. Now add them, equation number 1 plus 2. So on adding 1 plus 2, you will get, okay, so on 1 plus 2, you will get what? 1 upon V minus 1 upon U is equals to 1 upon F1. 1 upon V dash minus 1 upon U is equals to 1 upon F1. And here 1 upon V minus 1 upon V dash is equals to 1 upon F2. So this and this get cancelled out and 1 upon V, the downward positive sign and the up one per one is negative. 1 upon U is equals to 1 upon F1 plus 1 upon F2 plus 1 upon F2. Yes, this we have the relation. You can give it equation number 1. Now by lens formula, you have what? 1 upon V minus 1 upon U is equals to 1 upon F. So by comparing the right hand side of both the equations, you will have final relation 1 upon F is equals to 1 upon F1 plus 1 upon F2. Clear? Hmm. So yes, by adding you get this equation and by comparing it with equation number 4th, you will get finally 1 upon F equals to 1 upon F1 plus 1 upon F2. If you solve this one, like in resistance parallel combination, so F equals to F1 F2 upon F1 plus F2. Okay. Hmm. It means focal length are added in reverse of their uh, reciprocal form. 1 upon F equals to 1 upon F1 plus 1 upon F2. Now, if you convert it in the form of power, it will become total power, net power is equals to P1 plus P2. So total power is equals to sum of their individual powers. Yes. Now, second case, one lens is convex and another is concave. You know, if one lens f1 is the focal length of convex and f2 is the focal length of concave, then what? The focal length of convex mirror is positive. So you have to take 1 upon f1 is positive and focal length of concave mirror is concave lens is negative. So it will become 1 upon f1 minus 1 upon f2. So f is equals to f1 f2 upon f2 minus f1. Clear? For concave it is negative. Okay. Or if you're talking about power, then 1 upon f becomes power. Power is equals to p1 minus p2 because power of convex lens is positive and for concave lens it is negative. Okay. Yes. So there are three cases arises for the combination of convex and concave. Check here. We have 1 upon f equals to 1 upon f1 minus 1 upon f2. Okay. So it becomes f2 minus f1 upon f1 f2. f2 minus f1 upon f1 f2 1 upon f. So first case is when f2 is greater than f1. So when f2 is greater than f1, f2 means convex, f1 means convex and f2 means concave because it is negative. Clear? So when the focal length of concave mirror greater than focal length of convex mirror, so your final answer will be positive. Your final answer will be positive means 1 upon f is greater than 0. That is f is greater than 0. So your final lens will behave as like a convex lens. Clear? Because your resultant focal length will be positive. Okay. So it is given here when f1 is greater than f2. Yes, when f1 is lesser than f2, we have derived this one case when f2 is greater than f1 or f1 is less than f2. Then what? Where then f is positive, therefore combination would behave like a convex lens when focal length of a convex lens is smaller. Remember, when the focal length of convex lens is smaller, your lenses behave like a convex lens. Clear? Second case, when f1 is greater than f2. Yes, check. When f1 is greater than f2. So f1 is greater than f2, matlab a smaller number subtracted the larger number, then your focal length will be negative, less than 0, because this term will become less than 0. Means when focal length of convex lens is greater and focal length of concave lens is lesser, then your final combination of lens behave like a concave lens. Clear or not clear? Yes. So if f1 is greater than f2, then total f is negative. Therefore, the combination behave like a concave lens when the focal length of the convex lens is larger and concave lens is lesser. Clear? Now, when f1 equal to f2, when both the lens having equal power, then what will happen? When the both the lenses will have equal power or you can say equal focal length. So 1 upon f equals to 1 upon f1 minus 1 upon f2. They both having f1 equals to f2 have same value. So you can write 1 upon x minus 1 upon x. So 1 upon f equals to 0. They cancelled out 1 upon f equal to 0. Means f equals to 1 upon 0. You can say this is equals to infinity. Clear or not clear? Focal length equals to infinity means the combination of lengths of convex as well as concave. Yes, this is the combination of convex and concave. Now this lens behave like a transparent glass slab having infinite focal length. Whenever there is infinite focal length, means power is equals to 1 upon focus. Power is equals to 1 upon infinite equal to 0. Means 0 ability to bending the rays. Means this combination of lens behave like a transparent glass slab. Got it? So this behave like a transparent glass slab. Okay. Okay, see f1 equals to f2, then f equal to 0. So the combination would have like a plain glass plate or transparent glass slab. No refraction at all. Clear or not clear? So we have seen for the combination of lenses, total power becomes additive in nature. So P equals to P1 plus P2 plus Pn and so on. Clear? Now, if the lenses of the focal length f1 and f2 separated by a finite distance d, check here. There are the two lenses. Now, previously there are just in back to back in combination. But if there is a distance d, then the formula for the equivalent focal length is given by 1 upon f equals to 1 upon f1 plus 1 upon f2 minus distance d upon f1, f2. Learning facts. Then if the sum of the terms of right side is positive, this means the system of the lens behave like a convex. Yes, when total power or total focal length become positive, means the system having positive focal length means it behave like a convex. And if some of the terms on the right side is negative, means some system would behave like a concave lens because the total focus length will be negative. Clear? So this is the end of our lens and refraction. Now we are moving to our next topic. This is prism. Okay. Okay, student. So our next topic is optical instrument. We starting here to optical instrument, and our first topic in optical instrument is prism.